Named reactions are the language of organic synthesis. If you want to read research papers, understand reaction schemes, or follow discussions in a research lab, you need to know what these reactions do and why they work. In this video, we will cover 6 of the most important named reactions in organic chemistry. For each reaction, I will explain what it does, go through the mechanism step by step, and show you an example of how it is used in the synthesis of real drug molecules. By the end, you will not only recognize these reactions by name but also understand when and why chemists use them. So let's begin with the first reaction. We are starting with Suzuki coupling. At its core, Suzuki coupling connects two carbon atoms. Specifically, it joins an aryl halide with a boronic acid or boronic ester using palladium as a catalyst. The result is a new carbon-carbon bond between two aromatic rings. Now let's talk about what is the mechanism. It happens in three steps. First, oxidative addition. Palladium in its zero oxidation state inserts itself into the carbon halide bond of the aryl halide. Palladium just slides in there and breaks that bond. Now you have got a palladium complex. Second, transmetallation. The boronic acid, helped by the base in your reaction, transfers its aryl group over to palladium. Third, reductive elimination. These two carbon groups sitting on palladium get pushed together and a new carbon-carbon bond forms, and palladium is regenerated. The catalyst is ready to go again. What makes this reaction so powerful in pharma is that it works under mild conditions. It tolerates water and it's incredibly selective. You're not getting a mess of side products. A real example would be losartan. The blood pressure medication has a biaryl core that's built using a Suzuki coupling in its industrial synthesis. Now, if Suzuki coupling is the reaction for making carbon-carbon bonds, Buchwald Hartwig is its close cousin for making carbon-nitrogen bonds. In this section, an aryl halide reacts with an amine, and palladium helps join them together to form an aryl amine. Mechanistically, it follows the familiar palladium cycle. Palladium first undergoes oxidative addition into the carbon halide bond, then amine coordinates to the metal and is deprotonated by base, and finally reductive elimination forms the new carbon-nitrogen bond. For real drug applications, intermediates in the synthesis of imatinib, which is Gleevec, the landmark leukemia drug, use this type of carbon-nitrogen formation to install amine groups. Now let's move on to the Grignard reaction, one of the most important carbon-carbon bond forming reactions in organic chemistry. In this reaction, a Grignard reagent reacts with a carbonyl compound such as an aldehyde or ketone. The carbon attached to magnesium acts as a nucleophile and attacks the carbonyl carbon. This forms a new carbon-carbon bond, and after aqueous workup you obtain an alcohol. The key idea is that Grignard reagent behaves like a carbon nucleophile. It allows us to build larger molecules by forming new carbon-carbon bonds, which is why it is widely used in the synthesis of pharmaceuticals and other organic compounds. In terms of real applications, Grignard additions are used in the synthesis of terfenadine, an antihistamine, and in steroid-based API synthesis where you need to build a carbon framework efficiently. The Wittig reaction is a useful method for converting an aldehyde or ketone into an alkene. In simple terms, it replaces a carbon-oxygen double bond with a carbon-carbon double bond. The reaction uses a phosphonium halide which acts as a carbon nucleophile. The halide attacks the carbonyl carbon to form a four-membered intermediate called oxaphosphate. This intermediate then breaks apart to give an alkene and triphenylphosphine oxide. One important feature of the Wittig reaction is that it can control the geometry of the alkene. Stabilized halides usually give the E-alkene while non-stabilized halides mainly produce the Z-alkene. A great industrial example is that it is used widely in the synthesis of beta-carotene. And the retinoid drugs used in acne or skin treatments also relies on Wittig chemistry. The Diels Alder reaction is one of the most powerful ways to build six-membered rings. In a single step, it forms two new carbon-carbon bonds and can create several stereocenters with high selectivity. This reaction occurs between a diene, which has two conjugated double bonds, and a dienophile, which is usually an electron-poor alkene. They combine to form a six-membered ring through a concerted mechanism, meaning all the bonds form at the same time without any intermediates. For the reaction to occur, the diene must be in the S-cis conformation. In many cases, the endoproduct is formed preferentially because it is favored during the reaction. Now for the drug example, and this one is genuinely impressive. The total synthesis of Taxol, which is paclitaxel, one of the most powerful anti-cancer drugs we have and one of the most complex molecules ever synthesized in a lab, uses Diels-Alder chemistry to build its bicyclic core frame. The Mitsunobu reaction is a useful method for replacing an alcohol with another functional group while inverting its stereochemistry. This makes it especially valuable in medicinal chemistry where the correct 3D arrangement of atoms is often essential for biological activity. In this reaction, an alcohol reacts with a nucleophile such as carboxylic acid, phenol, or phthalimide in the presence of triphenyl phosphine and diad. Mechanistically, triphenylphosphine and diad activate the alcohol, converting it into a good living group. The nucleophile then attacks from the opposite side in an SN2 reaction, giving the product with inversion of configuration. This reaction is used extensively in the synthesis of nucleoside analogues, antiviral drugs, and prostaglandins derivatives, where getting the exact stereochemistry at the alcohol center is the difference between a drug that works and the one that doesn't. I have talked about 6 reactions in this video. In the next part of named reactions, I will share 6 another reactions. So see you in the next one.